Back again, everybody. So this is the last portion of this chapter, that is Michelson interferometer, and again it works on the principle of interference. So we'll discuss what is Michelson interferometer and what are the applications of Michelson interferometer. So basically, interferometer means we have discussed air wedge, we have discussed Newton's ring, and the third one we are going to discuss is interferometer. And an interferometer is an instrument in which the phenomenon of interference is used to make precise measurements of wavelengths or distances. It is basically used to calculate small distances or wavelengths of unknown sources of the light. It is much sophisticated and it gives you much good results as compared to Newton's ring arrangement. So, what is the principle of Michelson's interferometer? In Michelson's interferometer, a beam of light from an extended source is divided into two parts. And normally, from a single source, light is divided into two parts, and these two parts will be having arrangement is such that the two parts will be having equal intensity, and it is divided into two by partial reflection and refraction. And what happens next is that these reflected and refracted beams travel in two mutually perpendicular directions and come together after reflection and refraction from plane mirrors. These beams overlap on each other to produce the interference fringes, and this is actually the Michelson interferometer setup which we use in labs, and this is the schematic diagram of Michelson interferometer. That is how we are going to construct the Michelson interferometer. The schematic diagram of a simple Michelson interferometer is shown in the figure, and it consists of a beam splitter. You can see G, and you just listen to it carefully. It consists of a source of light, and the light from the source is rendered parallel using a lens, and this light is allowed to fall on the beam splitter G1. And we are having two mirrors, M1 and M2, and the mirror M1 and M2 can be adjusted so as to move back and forth. And here you can see the telescope for viewing the mirrors and the patterns. Okay, and in addition to this glass plate G1, there is a compensating plate G2 also. So what is the need of this compensating plate? I'll explain to you. And the beam splitter G1 is partially silvered plain parallel glass plate. The beam splitter G1 is partially silvered in the sense that one side is silvered. That is this region. The darkened region is silvered. So the light on reaching the glass plate enters the glass plate and it gets reflected from the bottom side of the glass plate. The ray enters, undergo refraction, and at the bottom side, which is a mirror, at this point it undergoes reflection. It undergoes reflection so as to reach the mirror M1, and the reflected light returns back from the mirror M1, passes through the glass plate G1, and we are having one more plate, compensating plate G2, and it is a plain parallel glass plate having the same thickness as that of G1. The two plates G1 and G2 are held parallel to each other and are inclined at an angle 45 degrees with respect to the mirror M2 and M1. That is the glass plate G1 and the compensating plate G2 is making an angle 45 degree with the mirror. Okay. So first the light gets split into two. The light on reaching the glass plates undergo refraction and undergo reflection. The reflected light passes once through the plate G1, reaches the mirror M1, undergoes reflection and passes again through the mirror through the glass plate G1, and it reaches the telescope. So my question is, how many times does the light passes through the plate G1? It passes through the plate G1. That is the reflected light this ray, the ray which is going to the mirror M1 passes through the glass plate thrice, while the ray which is transmitted, the ray which is refracted through the glass plate, this ray is reaching the mirror M1. M1 എന്ന മിററിലോട്ട് എത്തുന്ന റേ എന്താണ്? റിഫ്ലക്റ്റഡ് റേ ആണ്. ഇതിലൂടെ കടന്നു വന്ന് ഒരു പ്രാവശ്യം G1 പ്ലേറ്റിലൂടെ കടന്നു വന്ന് താഴത്തെ ബോട്ടം സൈഡിൽ നിന്ന് സിൽവേർഡ് പാർട്ടിൽ നിന്ന് റിഫ്ലക്ട് ചെയ്ത് G1ലൂടെ കടന്നുപോയി മിററിൽ റിഫ്ലക്ട് ചെയ്ത് തിരിച്ചു വന്ന് വീണ്ടും G1ലൂടെ കടന്നു പോയിട്ടാണ് ടെലിസ്കോപ്പിൽ എത്തുന്നത്. അപ്പൊ ലൈറ്റർ എത്ര ദൂരം ട്രാവൽ ചെയ്യും? റിഫ്ലക്റ്റഡ് ലൈറ്റർ എത്ര പ്രാവശ്യം ഗ്ലാസ് പ്ലേറ്റിലൂടെ? 3 പ്രാവശ്യം ട്രാവൽ ചെയ്യും. ബട്ട് ട്രാൻസ്മിറ്റഡ് ലൈറ്റ് റേ ആണോ? ഇതാണ് AB റേ പാത്താണ് ട്രാൻസ്മിറ്റഡ് ലൈറ്റ് റേ. അത് ഒരു പ്രാവശ്യം മാത്രമേ ട്രാവൽ ചെയ്യുള്ളൂ. അപ്പൊ ആ പാത്ത് കോമ്പൻസേറ്റ് ചെയ്യാൻ വേണ്ടിയിട്ടാണ് വി ആർ കീപ്പിംഗ് അഗെയിൻ വൺ മോർ ഗ്ലാസ് പ്ലേറ്റ് ഓഫ് ദ സെയിം തിക്നെസ് വിച്ച് is parallel to is kept parallel to G1 and it is named as G2. So the light ray passes through this glass plate again 2 times. On reaching the mirror M2, it gets reflected, again passes through the glass plate G2. So the light path through this glass plate, the transmitted ray will be having a light path through the glass plate 3 times, and the reflected ray also will be having the ray path through the glass plate 3 times. So that is the reason why we have kept another glass plate G2 which is parallel to G1. The mirror M1 is mounted on a carriage and can be moved exactly parallel to itself with the help of a micrometer screw. The mirror M1 is mounted on a carriage and can be moved exactly parallel to itself with the help of a micrometer screw. The distance through which the mirror M1 is moved can be read with the help of a graduated drum attached to the screw. Displacement of the order of 0.1 micrometer or 1000 angstrom can be easily read. That is, you can see the mirror M1 can travel to and fro, and the displacement of the mirror M1 can be read easily with the help of a graduated drum. It is attached to the screw. The plane mirrors M1 and M2 can be made perfectly perpendicular. Plane mirrors M1 and M2 can be made perpendicular M2 can be made exactly perpendicular to each other and mounted on the carriage, and can be made perfectly perpendicular to each other with the help of spine screws attached to them. The interference band thus obtained. So light traveling, reflected light reaches the telescope. Similarly, the transmitted light which is reflected from the mirror M2 also reaches the telescope. And you can see the interference pattern or interference bands can be observed in the field of view of the telescope. I hope it is clear. 2 mirrors, 2 glass plate, 1 source, 1 lens. Motion of the mirror M1 and M2 can be adjusted, and a telescope to view the bands, interference band. So the monochromatic light from an extended source S is rendered parallel with the help of a collimator lens, and it is made to incident on the beam splitter G1. It is partially reflected at the back surface of G1. It is reflected at the back surface of the G1 so as to have a ray path AC, and partly transmitted along AB. The beam AC travels normally towards the plane mirror M1, and it is reflected back along the same path and comes out along AT. The light ray getting reflected from G1 reaches M1, reflects back and reaches the telescope T. The beam AC travels normally towards the plane mirror M1 and is reflected back along the same path and comes out along AT. The transmitted beam travels towards the mirror M2 and is reflected along the same path. It is reflected at the back surface of G1 and proceeds along AT. The two beams received along AT are produced from a single source through division of amplitude and are hence coherent. The two beams received along AT are produced from a single source through division of amplitude. Okay, that is understood. The light is initially coming from an extended source S and it gets split. So normally I can say that they are coherent light. And the superposition of this coherent light with a path difference produces interference pattern. And in figure 15.23, it is clearly seen that a light ray starting from the source S and undergoing reflection at the mirror M1 passes through the glass plate that I have mentioned earlier. The light ray reaching the mirror M1 passes through the glass plate G1 3 times. On the other hand, in the absence of the glass plate G2, the ray which is reflected at the mirror M2 travels to the glass plate G1 only once. For compensating this path difference, a compensating glass plate G2 of the same thickness is inserted into the path AB and is held exactly parallel to G1. So it is clear, the concept is clear. And if we look into the instrument from T, we see that the mirror M1 in addition. So and we are looking at the instrument through the telescope T, and what you can see is that we can see the mirror M1, and in addition we can see a virtual image of mirror M2 that is named as M2 prime. Depending upon the position of this mirrors, the image M2 prime may be in front or behind or exactly coincident. So you can adjust the position of M1 and M2 prime such that you can see the virtual image of M2, that is M2 prime, which could be either along the same coincident position of this M1, or it could be behind M1, or it could be in front of M1. Okay, hope it is clear. So next is circular fringes. Circular fringes are produced with monochromatic light from the mirrors M1 and M2 are produced with monochromatic light from the mirrors M1 and M2 are exactly perpendicular to each other. The origin of the circular fringe can be understood as follows. Now we are going to discuss how we are getting the circular fringes. If you are looking at the instrument from okay, and if you are looking at the instrument, from T, we see the mirror M1 directly, and in addition we will see the virtual image of the mirror M2, that is M2 prime, formed by the reflection in the glass plate G1. And normally in the glass plate G1 there will be reflection from the mirror, and you can see that also. It means that one of the interfering beams come from M1 and other beam appears to come from the virtual image M2 prime. The situation is similar in the case of an air film enclosed between the mirrors M1 and M2 prime, with the difference that in case of a real film, air film between two surfaces, multiple reflection take place. In this case only two reflections take place. Okay, അപ്പോൾ നമ്മൾ എങ്ങനെയാണ് നോക്കുന്നത് വെച്ചാൽ നമ്മൾ ഇവിടെ നിന്ന് നോക്കുന്ന സമയത്ത് ടെലിസ്കോപ്പിലൂടെ നോക്കുന്ന സമയത്ത് നമുക്ക് എന്ത് ചെയ്യാൻ പറ്റും, ഈ മിറർ ഒരു ഇമേജ് ഈ ഗ്ലാസ് പ്ലേറ്റിലൂടെ നമുക്ക് കാണാൻ പറ്റും. അപ്പോൾ നമുക്ക് ഫീൽ ചെയ്യുന്നതാണ് രണ്ട് മിറേഴ്സ് ഉണ്ട്, ആ രണ്ട് മിറേഴ്സിന്റെ ഇടയിലും ഒരു എയർ ഫിലിം ഉണ്ട്. ആ എയർ ഫിലിം ഉണ്ടാക്കുന്ന ഇന്റർഫറൻസ് പാറ്റേൺ ആണ് നമ്മൾ ഒബ്സർവ് ചെയ്യുന്നത്. ഓക്കെ, and if the two arms of the interferometer are equal in length, then what happens? The M2 prime image of the mirror M2 coincide with that of the mirror M1. If M2 prime and M1 do not coincide, then the distance between them is finite. M2 prime M1 is D. Now if a light ray comes from a point S and is reflected by both M2 prime and M1, the observer will see two virtual images due to reflection. Okay, now if the light ray coming from a point S and is reflected by both M2 prime and M1, the observer will see two virtual images of S1 due to reflection by at M2 prime and S2 due to reflection by M1. That is understood. The virtual images are separated by a distance 2D. And if the observer looking to the system at an angle theta, the path difference between the two beams will be, and it is understood. If there is an air film, the extra path difference will be 2D cos theta, and if there is a phase change occurring due to reflection, an additional path difference of lambda by 2 also occur, and that we have discussed 2D cos theta plus lambda by 2. The same thing is happening here also. So I can put the condition for constructive indifference and I can put the condition for destructive indifference. Okay, the distance between these two mirrors is M2 prime, M1 prime is D. Actually, if this is M1 and this is M2 prime and the distance between them is D, what happens? The light ray passing through M1 reaching M2 prime get reflected. Means D ദൂരത്തിലുള്ള എയർ ഫിലിമിലൂടെ എത്ര പ്രാവശ്യം ലൈറ്റ് റേ ട്രാവൽ ചെയ്യും? It travels 2 times. And if it is instantly at an angle theta means there will be cos theta angle. And here the refractive index, that is, it is an air film, assumed to be an air film, that is refractive index is mu is equal to 1. And again, if there is phase changes occurring due to reflection, pi phase change corresponds to a path difference of lambda by 2. So the total path difference will be 2D cos theta plus lambda by 2 is equal to m lambda. M is equal to 0, 1, 2, 3, etc. For a given mirror separation D, a wavelength lambda and order m, the angle theta is constant. This means that normally the light ray passing through M1 and M2 will travel in a distance 2D, and it is inclined at an angle theta, means the path difference will contribute 2D cos theta, since refractive index of air is 1 here, and there is a phase change rare to dense reflection. There occurs a phase change by corresponding to a path difference lambda by 2, so it will be 2D cos theta plus lambda by 2. Corresponding to brightness, it will be m lambda. So what happens is that if lambda, m, d are constant, then theta is also be a constant for a mirror separation D. Then the fringe shape will be circular, and these fringes are called the fringes of equal inclination. And if both the mirrors M2 prime and M1 coincides, D will be 0. So what happens is that the path difference will be lambda by 2, corresponding to a dark corresponding to minimum at the coincidence position, and the center of field will be dark at this point. And if one of the mirrors is now moved through a distance lambda by 4, what happens? The path difference changes by lambda by 2. If mirror is moving through a path difference, that is, two mirrors are there, one mirror is moved through a distance lambda by 4, the path difference contribution will be what? 1 lambda by 4 in the forward direction and 1 lambda by 4 in the backward direction. So it will be lambda by 4 plus lambda by 4. It will be lambda by 2. So if one of the mirrors is now moved through a distance lambda by 4, the path difference changes by lambda by 2, and already there is a path difference of lambda by 2, and here I have already mentioned it. When D is equal to 0, when both of them coincides, it will be lambda by 2, corresponding to a darkness or destructive indifference or minimum. Again, if one of the mirrors is moving through a distance lambda by 4, path difference will be lambda by 2, that is lambda by 2 plus lambda by 2, it will be lambda, corresponding to a brightness or maximum. Again, if you are moving the mirror through lambda by 4, path difference will be added by lambda by 2 again, so there will be a minimum, then again lambda by 4 means a maximum, and this process will go on like that way. Therefore, a new ring appears in the center of the field of view each time the mirror is moved through a distance lambda by 2. As D increases, what happens? New rings appear in the center faster than the rings already present, and the field becomes more crowded with thinner rings. Okay, that is understood as D increases. And when D is made smaller, the rings contract and they disappear at the center. So what do you mean by the concept of localized fringes? When two of these mirrors are parallel and they are moved against each other, they are coinciding. We have discussed all those positions. Now next we'll assume the condition where the mirrors are not kept perpendicular exactly to each other. Actually one mirror is here, one mirror M1 is here, another mirror M2 here, and they are exactly perpendicular to each other. So if you observe the image M2 prime, M and M1 which will be exactly parallel, right? And if I am tilting one of these mirrors slightly, then what happens? In this case, the air path between them is wedge shaped. It could be tilted in this form, it could be in this form, it could be in this form. And the fringes, and if it is moving to a tilted position, the wedge shaped film will be formed. And we have already discussed what is the nature of the wedge shaped film and nature of the fringes. Fringes will be straight line fringes. The position of any bright fringe is taken up. Okay, that is understood. If one of the mirrors is moved, the fringes also move the field of view, and the position of any particular bright fringe is taken up by the next bright fringe, and the number of fringes can be, and we can see through the telescope, and we can adjust the position, and we can count the number of fringes. And if we have counted m number of fringes move across the field of view, when the mirror M1 is made to move through a distance d, I can say that d is equal to m times lambda by 2. How the lambda by 2 condition is obtained, it is clear. At the center, path difference, when both of them are coinciding, it starts with lambda by 2. Then it is increased by lambda by 4, producing a path difference lambda by 2 and causing darkness and brightness accordingly. So I can say the number of fringes, one fringes moved means 1 lambda by 2, two fringes moved means 2 lambda by 2, n fringes is moved means m lambda by 2. From this I can calculate the wavelength of the light also, 2d by m. And next we are going to discuss the white light fringes. It is written here as white light fringes. Okay. Instead of monochromatic source of light, if we are using the white light, what happens? The fringe pattern obtained will be colored fringes with a central dark fringe. And in observing these fringes, the mirrors are slightly tilted and you can see the changes. Okay. And the position can be best located with monochromatic light when the fringes become straight. Then a very slow motion of mirror M1 in this region using white light will bring fringes in the field of view. And a central dark fringe is surrounded by 8 to 10 colored fringes on either side are observed. And it is clear. So next is, what are the applications of Michelson interferometer? Michelson interferometer can be used to determine the wavelength of a given monochromatic source of light. It can be used to determine the difference between the wavelengths of the two neighboring wavelengths or resolution of the spectral lines. It can be used to determine the refractive index and thickness of various thin transparent materials, and many applications are there. And it is also used for the measurement of a standard meter in terms of wavelength of light. It is used in the measurement of the standard meter in terms of wavelength of light. So Michelson interferometer is used to determine the wavelength of light from a monochromatic source of light. The monochromatic source is kept at S, and if the mirrors M1 and M2 are exactly perpendicular, circular fringes are obtained, and it is understood. If the mirror M1 is moved forward or backward, the circular fringes appear or disappear. Now as the mirror is moved through a known distance d and the number of fringes appearing at the center is counted. Suppose d1 is the initial thickness of the air film between the mirror M1 and the image M2 corresponding to the bright fringe of order M1 and D2 thickness, and it is clear from this equation. Suppose we are having D1, if there is separation, if the mirror M1 is moved through a distance D1, M1 fringes appear. We are having already the equation D is equal to M lambda by 2, or lambda is equal to 2D by M. So 2D is equal to M lambda. And if the mirror is moved through a position D2, we can write if Mn fringes passes the field of view, I can write 2D2 is equal to Mn lambda. Okay. And D1 corresponds to the thickness of the air film which is formed between the mirror M1 and the image of the mirror M2, that is M2 prime. Okay. So I can get by subtracting 2 into D2 minus D1 is equal to Mn minus M1 into lambda. From that I can calculate lambda is equal to 2D minus N, where D is equal to D2 minus D1 and N is equal to Mn minus M1. And next is determination of the difference in wavelength of the two waves. Suppose for the same separation, that is 2D, I am using two wavelengths of light, and lambda 1 wavelength corresponds to number of fringes M1, and lambda 2 wavelength corresponds to M2 number of fringes, where M2 is equal to M1 plus 1, and I can substitute it here. 2D is equal to M1 lambda 1 is equal to M1 plus 1 lambda 2, right? That is mth order of one wavelength corresponds to M1 plus M plus 1th order of the other wavelength. Okay, that is the relation. So normally substituting for that, I can find out M2 is equal to M1 plus 1. So M1 is equal to lambda 2 divided by lambda 1 minus lambda 2. And substituting it in this equation, we have obtained M1, and M1 into lambda 1 is equal to 2D. That is 2D is equal to lambda 1 lambda 2 divided by lambda 1 minus lambda 2. From that I can obtain lambda 1 minus lambda 2 is equal to lambda 1 lambda 2 divided by 2D. Okay, so delta lambda is equal to lambda 1 lambda 2 divided by 2D. If lambda 1 is equal to lambda 2, it will be lambda square by 2D. Hope it is clear. If I'm increasing the distance between this, I'm just changing the position of the mirror M1. It indicates the condition that M1 and the mirror position change M2 എന്ന് പറയുന്ന മിററിന്റെ വിർച്വൽ ഇമേജ് M2 പ്രൈം അവിടെ കാണും. അപ്പൊ M1 M2 തമ്മിലുള്ള ദൂരം D ആണ് ഞാൻ ചേഞ്ച് ചെയ്തതെന്നുണ്ടെങ്കിൽ ലൈറ്റ് ട്രാവൽ ചെയ്യുന്ന ദൂരം എന്ന് പറയുന്ന പാത്ത് ഡിഫറൻസ് 2D ആവും. ആ 2D കണ്ടീഷൻ വെച്ചിട്ടാണ് നമ്മളിങ്ങനെ ആ കഥകളെല്ലാം വന്നിട്ട് ഇവിടെ എത്തിയത്. എന്നിട്ട് നമ്മൾ എന്ത് പറയുന്നു, രണ്ട് വേവ് ലെങ്ത് ആണ് ഉപയോഗിക്കുന്നതെന്നുണ്ടെങ്കിൽ ഒരു വേവ് ലെങ്ത്തിന്റെ M1th order corresponds to M1 plus 1th order of the next wavelength, that is M2. Then we can find out the difference in wavelength of these two sources that we are using. Hope it is clear for you. So we have completed this chapter, that is Michelson interferometer. You just go through. I'll send you the PPT and I'll send you the link. You go through the text, view this. If any doubts, you can come to me. So in next class we'll discuss diffraction.